In this lecture we will talk about problem of observer design for a very special class of discrete time nonlinear systems. Okay, so let's first be precise about what we mean when we use the word observer. Okay, in different contexts it may be used in similar but different meanings. Okay, but in our context, by an observer we mean the following. So given discrete time system, okay, x plus equals f of x, and for that system we collect certain measurement which we denote by y, and y, the measurement, the output, is some function of the state, let's say, okay, with f and h continuous matrix. Okay, the system x hat plus equals g of x hat and y. So this is a system we can consider this as a system with the input, and well, x hat is the state of the system, and y we can consider as the input to the system, and this y, input to the system, the observer system, is the measurement that we collect from the actual original system. Okay, with G and mapping of the sort Rn to Rn is said to be an observer for the system x plus equals f of x with output y equals h of x if solution of following coupled system in R2n, okay, one n for the order of the origin system, and the other n is coming from the order of the observer system, and x plus equals f of x and x hat plus equals g of x hat, and the input of the second system, the observer system, is the output of the first system, y, and y is determined by this mapping h. So we have this system. So x system is autonomous, it depends only on its own state, but the evolution of the estimate system, okay, or the observer system, or the observer state, depends not only on its own state, but also on the evolution of the original system, x state. Okay. Now, such a system is said to be an observer if the state of the observer system converges to the state of the original system x plus equals f of x. Okay. Okay. Once again, given the system with such and such is said to be an observer if the solution of this coupled system satisfies the following convergence property, as k goes infinity for all initial conditions x0 and x hat 0. Okay. Given the system, you construct the observer subsystem in such a way that when you run these two systems together, starting from arbitrary initial conditions, it's always the case that the difference between the actual state and its estimate converges to 0. Okay, if that is the case, then this is said to be an observer system. Okay, for the for the given system. Now the question is why this is an interesting problem or an interesting construction. The reason has a strong practical motivation. Suppose that this models some actual system in the real world. Okay? And for some decision or optimization process, what we require is we require the entire state, okay, of the system. But the problem, which is a practical problem, is that you cannot directly measure all the states of the system. Okay, so you can only measure the partial state of the system, and the reason for that could either be that measuring all the states would mean a lot of sensors, and that would be quite expensive. That would be a quite expensive thing, for instance, or sometimes it's simply impossible to measure directly certain states, okay, because of consider some the temperature as one of the state variables of your system, and the temperature is the temperature we're talking about is the temperature inside the piston of some engine. Okay, so inside the piston, the conditions are very harsh. You cannot put a sensor inside that, or if there's a sensor that would work in such harsh environment, it would be a very, very expensive sensor. So what we want to do is, if you can get away with not using a sensor, then we would not. And in that case, what we would do is, from the cheap measurements, okay, from the available measurements, we try to construct the state of the system. Okay, and that we do usually using another system which we call observer system, and that observer system collects the measurements from the actual system, and it has its own state. It runs. Initially it produces some, let's say, meaningless estimates, but eventually, if it's a successful observer, the estimate of the state becomes better and better, in the sense that the estimate produced by the observer and the actual state, the difference between those two vectors converges to zero. Okay, so the most widely used observer construction, if it's possible to use it, is Leuenberger observer, which is applicable to linear systems. So let's remember about that construction. Okay, we call the Leuenberger observer for linear systems. Okay, so we have the system x plus ax, and the output or the measurement is a linear function of the state y equals cx. And for this system, we use the following topology for our observer system. Okay. X hat plus equals a x hat, and then to this we add the error signal, and error by error signal we mean some gain, okay, which multiplies the difference between the actual output and the would-be output, namely y minus cx hat. This cx hat we can call y hat in a sense. Okay. Now, this construction is very easy to analyze. All you have to do is define the error as x hat minus x. Okay, and then the error dynamics can easily be written as e plus equals x hat plus minus x plus. X hat plus is this, so this is our observer system. And this is the actual system. The actual system is representing some system in the real world, whereas the observer system usually runs in our computers. So the error dynamics are this equals a x hat plus l y minus cx hat. Then we have x plus, which is ax. Okay. Then we can write that as a x hat minus x plus L cx minus cx hat, because y equals cx. That can be written as a minus LC times x hat minus x. Okay, and x hat minus x was no other than the error signal. Therefore, that equals a minus LC times error. Okay, therefore, aerodynamics depends only on this difference, x hat minus x, not independently on x hat and x. Okay. Now, in order for this observer to be called an observer or a successful observer, what we require is x hat catches x as time goes on. In other words, since the error is x hat minus x, we require, if our observer works properly, what's going to happen is this error converges to 0. Now that aerodynamics is a linear system, therefore the convergence check is straightforward. All you have to do is you look at the eigenvalues of the matrix A minus LC. Now, dynamics E plus equals A minus LCE, the aerodynamics, imply that if the eigenvalues of the matrix A minus LC satisfy the stability condition for discrete time, which was that they're all with magnitude strictly less than 1, then we know that this system is, the origin of that system is globally exponentially stable. In other words, the error goes to 0 as k goes to infinity. That is x hat k minus xk, because this difference is what we're defining as the error converges to 0. Hence, design an observer through the Lundberg observer topology or Lundberg observer construction. Choose the observer gain L. Okay, we're talking about this matrix that appears in our observer system, which must be an n by n matrix, such that eigenvalues of A minus LC satisfy the stability condition. Okay. Now the question, of course, is under what conditions on the system parameters A and C we can find an L such that the eigenvalues are with strictly less than unity magnitudes. Okay. So this is an important question. When can we choose such L? Okay. The answer is when the system is observable. In fact, even a weaker condition is sufficient for us to be able to choose such an L, and that Beaker condition is studied under innate detectability. So when the pair CA, or when this system is detectable, it's possible to choose the observer gain so that the aerodynamics are with stable eigenvalues. Okay. And detectability simply means that there are no unstable modes in the unobservable subspace of the system. Okay, having remembered the famous observer construction for linear systems, now we're going to talk about the observer construction for nonlinear systems. First of all, it's very difficult for a general nonlinear system to design an observer. Okay, so it's still a largely open problem. So you have to make some restrictive assumptions on your nonlinear system in order to be able to figure out to design a working observer. And in this lecture, we will be considering one such special case. We're going to make some very restrictive assumptions, but nevertheless, there are some important systems in the real world that satisfy those restrictive assumptions. So therefore, it's worthwhile to study that system, even if it's a very special class of system. So for that special class of system, we're going to propose an observer construction. Okay, and we're going to perform the stability analysis for the observer dynamics. So the observer that we'll talk about is invented by Professor Torkel lab in 1980s, and it's quite an appealing design because it's very simple. Okay, so let's now talk about GLAD's observer. So the system that we consider has the form that we consider so far: x plus f of x and y equals h of x. Okay. Now we're going to make certain assumptions on our system for which we are to design an observer. The assumptions are as follows. A1, the output y is scalar. Okay, so that's one of our assumptions. The second assumption is that the right-hand side of the system is invertible. The inverse mapping exists. Okay. So we call such f an invertible f. Okay. And perhaps most importantly, for each C in Rn, the following equation has always a solution, and the solution is unique. And the equation that we're talking about is the following. Okay. Now you construct a vector. And in Rn, by the way, remember that f is from Rn to Rn, and h is from Rn to Rn in general. But now we're considering a scalar output, therefore h is a function from Rn to R. Okay. And inverse mapping f is scalar. Okay. Excuse me, it exists. Okay. So this mapping is 1 to 1. And for the last assumption, we assume that this equation h of x, h of f inverse of x, h of f double inverse of x, and so on, h of f n minus first inverse of x. Okay. Now, since alpha is a scalar, this h of x is a scalar, h of f inverse x is also a scalar. So basically what we're doing is we're stacking these n functions of x, okay, scalar functions, into a vector. Okay. Now the unknown is x here, and for the right hand side we put any vector in Rn. Okay. Now the assumption, third assumption, is that this equation, this is known and x is unknown, always admits a unique solution x for each psi, has a unique solution x in Rn. Okay, and that's our third assumption. Now, under these assumptions, okay, Professor Glad proposes the following observer topology. Okay, here is the observer. Dynamics x hat plus equals f of eta. Okay, so this is system 1, the given system, and this is our observer system. Let's call it 2, of course. In this form, it's meaningless without defining what eta is, and eta is computed at each time through the following equation, where eta, itself a vector in Rn, solves at each time the following set of equations. H eta equals y. H of f inverse eta equals h of f inverse x hat. X hat is the x hat is the current state of the observer. H of f double inverse eta equals h of f double inverse of the state of the observer, and so on. H of f n minus first inverse eta equals h f n minus first inverse x hat. Now this set of equations we call set star. Okay. Note that first of all, this equation has always a unique solution, okay, eta, given y and x hat, because of our third assumption. Okay. In this case, what we do is you stack all these scalars on the right hand side into a vector, and that vector is your psi vector at that particular time, and then this unknowns are collected on the left hand side, and you obtain this equation, okay, or the formula of that equation, and by assumption 3 that equation always has a solution. Okay. Okay, so at any given time, you set the right-hand side by the givens, and then you compute eta by solving this equation. And there's always a unique eta that solves that equation. And once that eta is determined, you apply it, you pass it through f, and f is the mapping that appears in the original system. And what you obtain is the value of your estimate state at the next time instant. Okay, and then with the new measurement, you go on to figure out the next estimate and so on. Okay, so note that. Eta is a function of both x hat and y. That is, eta is eta of x hat and y. Y is coming from the original system, it's h of x. Then the remaining entries are coming from the state of the observer. Therefore, the eta that you have to compute at each time, that each time will be a function of x hat and y. Okay. Here we have system 1, and here we have the observer system, system 2, which is x hat plus equals f of eta. F is the same f that appears in the system equation, and eta that the observer computes eta by solving this set of equations at each time. Okay, and this set of equations always admits a solution, and that solution is unique because of the assumption that we made on the system. Now, here is Glad's theorem. System 2 is an observer for the given system, system 1. In particular, it is a deadbeat observer in the sense that the convergence of x hat x is exact in finite number of steps. Okay. In particular, for all initial conditions, we have x hat k equals xk. Okay, so the estimate exactly, the observer state exactly estimates the actual state after n steps. Okay, for all k greater than or equal to n. This type of observer, where the convergence is exact and appears and occurs in finite time, where equality x at k equals xk is achieved in finite time is called maybe you heard, it's called deadbeat observer. Okay, so Glad's observer therefore is deadbeat type observer. Now let's prove this theorem. Which is sort of not that of a long proof. our proof, to keep the notation simple, we're going to introduce some shorthand symbols. Let's use the following shorthand notation. Okay. To get rid of parentheses, instead of calling x of k, we're going to call this as x sub k. Okay, so this is the value of the state at discrete time k. Initial condition starts for initial time is k equals 0. Likewise, x hat sub k is this, eta sub k is this, and further drop the parentheses. And write x k plus 1 equals, instead of f in parentheses x of k, just write f x sub k. Okay. And yk h x sub k, and x hat k plus 1 is f of eta, and we write that as f eta sub k. Okay. Now what we want to show therefore in this new notation is x hat k equals x of k for k greater than or equal to, and if you can show that, then you will have proven the theorem. Okay. Now start from time k equals 0, the very first time, okay, the initial time. Now this is our set of equations where the observer solves at each time. So therefore it will start solving at time k equals 0. It will solve for eta, and the eta that it will compute will be eta 0, and that eta 0 it will use to figure out the value of the estimate at the next time instead, k equals 1. Okay. So at time k equals 0, star implies that these equations are satisfied, and here at k equals 0 we have eta 0 for etas, this is y0, and this is x hat 0. Okay. So that implies, let's look at the first equation only, h eta 0 equals y at k equals 0. So what's y? Y is h of x at k equals 0. Okay. And then also eta satisfies some other things, but we don't care about those other things. Okay, for k equals 0. Then we move on to next time, k equals 1. Now the observer solves this equation, and it produces an eta, that's eta 0. It plugs that eta 0 here and computes x hat 1. Okay. And then at time k equals 1, it resolves this equation. So in that case, at time k equals 1, what we have is h eta 1 equals h eta 1 equals y1, and y1 is hx1. Okay. As for the second equation or equality, that's also satisfied. What we have is hf inverse eta 1. Okay, that equals hf inverse x1 hat. So eta 1 must be such that it should satisfy this. And that implies what? We can write this as hf inverse. What's x1 hat? It's f of eta 0. Okay. So f inverse f, they cancel one another. We're talking about h of eta 0. H of eta 0 is h of x0. And x0 is f inverse of x1. H of f inverse x1, because x1 is f of x0. Remember that we assume f inverse exists. Okay? And the remaining equalities, equations, we don't care, at least for time k equals 1. Okay, and then let's move on to k equals 2, and then the pattern becomes more or less apparent, and we can just jump to k equals n minus 1. Time k equals 2. We have h eta 2 equals y2, and y2 is h of x2. Okay. Again, coming from equation star, set of equations star, hx2. And then we have hf inverse eta 2 equals hf inverse x2 hat. Okay. And that's hf inverse f eta 1. Okay, because x2 hat is f of eta 1. Okay, coming from the observed dynamics. This f inverse and f, they cancel. What we have is h of eta 1. What's h of eta 1? H of eta 1 is h of x1. Okay, and what's h of x1? It's h of f inverse x2, because x2 is f of x1, therefore x1 is f inverse of x2. Okay. So therefore we have h f inverse eta 2 equals h f inverse x2. Then h f double inverse eta 2 equals h f double inverse x2 hat. Okay. And that equals h f double inverse f of eta 1, and that's h f inverse eta 1, and h f inverse eta 1 is h f inverse x1, h f inverse x1, and x1 is f inverse x2. So we have f inverse, that means f double inverse x2. Okay, so we have h f double inverse eta 2 equals h f double inverse x2. Okay, and then you go to time k equals 3, time k equals 4, and so on. By doing that, you reach the time k equals n minus 1. N is the order of the system. Okay. Time k equals n minus 1. By the same reasoning, and always resorting to the set of equations that we denoted by star, we can write that time k equals n minus 1. N minus 1 equals hx n minus 1. hf inverse n minus 1 equals hf inverse x n minus 1. hf n minus 1 many times inverse n minus 1 equals hf x n minus 1. Okay, at time k equals n minus 1, all we have the following right hand side for our equation. Okay, and the observer has to solve this equation. Now clearly, if you plug in eta n minus 1 equals x n minus 1, automatically the equation is satisfied. And we know that the solution to that equation is unique. Therefore, the solution must be that eta n minus 1 equals x n minus 1. Okay. So eta n minus 1 must equal x n minus 1 by the third assumption, A3. Therefore, xn hat equals f of eta n minus 1. So this is the observed dynamics. Eta n minus 1 is computed solving this set of equations, and we have shown that the solution to that set of equation is xn minus 1. And xn x hat n, therefore is f of eta n minus 1. That's f of x n minus 1, and f of x n minus 1 is no other than x n. Okay. So at k equals n, therefore we have x hat n equals x n. The estimate becomes exactly equal the state to be observed. And it's not difficult to see that once the observer state catches exactly the original system state, then it never lets it go. Equation star, or set of equations star, guarantees that from that point on, the two states will always remain the same for all k larger than or equal to n. And that's the end of our proof. Okay, let's apply this observer construction to some numerical example. Discrete time nonlinear model for chaotic oscillator. Okay, that's by Professor Schuon. And the dynamics are given as x1 plus equals 1 plus x2 minus a x1 squared, x2 plus equals b x1 plus x3, and x3 plus equals minus b x1. Okay, so this is our system, a third order nonlinear discrete time system. Okay, now this implies that f of x for our system is 1 plus x2 minus a x1 squared bx1 plus x3 and minus bx1. Okay, so that's our right hand side. It turns out that for non-zero b, this map is invertible. It's not difficult to figure out the inverse. And I leave it as an exercise. The inverse reads the following: 1b x3 minus 1 plus a over b squared x cubed x3 squared plus x1, and the third entry is x2 plus x3. In fact, if you take this vector and put it here, you can pass it through f, what you obtain is identity, that is x1, x2, x3. Or you can do the same thing in the reverse direction. Still you obtain x1, x2, x3, which would prove that this and that, they're inverses of fundamental. Okay, so we have a third order nonlinear discrete time system where the right hand side is invertible. And suppose that for this system we measure the third state variable. Okay, that is, at each time we measure x3. And what we want to do is we want to construct an observer using glass construction, so that from that x3 information we generate an estimate which catches the actual state in that neat fashion. Okay, so for this system Suppose we can measure y output x3. Therefore, this is how we define our mapping h. H of x is third state variable x3. Okay, design an observer using glass construction. X hat plus equals g of x hat y. So we have to figure out what that mapping g is. Okay, so let's do that by glass construction. Apply glass method. Okay. By which we mean we have to solve at each step for eta. Eta 1, eta 2, eta 3 transpose. This is our eta vector. In H eta, H f inverse eta, H f double inverse eta equals, okay, the very first entry is the measurement y, and then the remaining two entries are H f inverse x hat, H f double inverse x hat. Okay, so at each time we're going to construct this vector, which is known because we know the output for measurement and we know our own state, the observer state x hat. We construct this vector and then we equate this thing here where the eta is unknown to that vector. And we want to figure out that eta. Once the eta is figured out, the value of the estimate, the observer state at the next time instant is simply that eta passed through our function right hand side f. Okay, so we have already f inverse and h is the third entry of the vector. Therefore h of eta and h of f inverse eta, we know what they mean. So the only thing that we don't know at this point is f double inverse. Okay? And what we need is h of f double inverse to be able to solve this equation. So we need f double inverse. In fact, what we need is only the third entry of f double inverse because h only picks the third entry. Okay? So let's try to answer that question. F double inverse x equals what? Because that's something we need for our construction. So f double inverse of x equals, okay, we don't care about the first and second entries. As for the third entry, we have this for f inverse. We apply to this vector once again this mapping f inverse, and we look at the third entry. So the third entry is x2 plus x3. So if you apply once again f inverse, what you have is, excuse me, okay, you have to add the second and third entries, okay, of f inverse. So this is our second entry and this is our third entry. Therefore this plus that is the third entry of our f double inverse x. Okay. Minus 1 plus a over b squared x3 squared plus x1 plus x2 plus x3. Okay, so that's the third entry of f double inverse. Therefore, h of f double inverse x equals minus 1 plus a over b squared x3 squared plus x1 plus x2 plus x3. Okay, now we're ready to solve this equation because we know h f inverse and h f double inverse. So H eta, HF inverse eta, HF double inverse eta equals, for the given H and F, H of eta, remember that eta is eta 1, eta 2, eta 3. Okay. H of eta is, H picks the third entry, so we're talking about eta 3. So this is eta 3. This is F inverse. Third entry of F inverse is x2 plus x3. Therefore, here we have eta 2 plus eta 3. And here we have H F double inverse of x. Instead of x, we now have eta. Therefore, we have minus 1 plus a over b squared x3 squared plus x1 plus x2 plus x3. Excuse me, this should be etas. Eta 3, eta 1, eta 2, eta 3. Okay. So that's this vector, and then we want to solve this by equating that to. Okay, the first entry equals y. Okay. And then the second entry equals h f inverse x hat. Therefore we simply have x2 hat plus x3 hat. And for the third entry we simply have minus 1 plus a b squared x3 hat squared plus x1 hat plus x2 hat plus x3 hat. Okay, now that's, in this equation, the right hand side is known. We know y and we know all the x hats. And from that knowledge, we have to figure out eta 1, eta 2, and eta 3. Okay, and once we have that, we can construct our eta vector, and that vector passed through F will give us the observed state at the next times. Okay, so let's solve it. Clearly, eta 3 equals y. Okay, so that was easy. And then eta 2 equals this thing minus eta 3, and eta 3 is y, therefore eta 2 equals x2 hat plus x3 hat minus y. Eta 2 equals x2 hat plus x3 hat minus y. Okay. Now that we want to express all etas in terms of hat x's and y. Finally, for eta 1, what we have is this thing equals that. At this point, we know eta 2 and eta 3 in terms of y and x hat. Therefore, we can write simply the following. First of all, eta 2 plus eta 3. You add those two things, the y's will cancel. You have x2 hat plus x3. Okay? And that will cancel this x2 hat plus x3. And what remains is then eta 1 equals x1 hat b squared x3 hat squared minus a over b squared y squared. Okay, because eta 3 is y. Okay, so we have figured out, we solved the equation that has to be solved at each time by the observer. Then all that remains is collect that eta and pass it through the F, the right hand side of the system, and you have your observer dynamics. Okay. Therefore, eta, which is a function of x hat and y, equals this. Eta 1 equals x1 hat plus a over b squared x3 hat squared minus eta 2 is here, x2 hat plus x3 hat minus y, and finally eta 3 is y itself. Once we have the eta, all that remains to write down the observer dynamics is pass that eta through the mapping F. Finally, the observer dynamics, read x hat at the next time instant equals f of eta, and f was 1 plus eta 2 minus a eta 1 squared b eta 1 plus eta 3 and minus b eta 1, and etas are here, eta 1, eta 2, eta 3. And then if you want to write the entire dynamics, okay, without etas, directly in terms of x hat and y, this is what the thing becomes. It becomes a little complicated, but remember that construction itself, the idea behind construction was very, very simple. x2 hat plus x3 hat minus y, that's eta 2. Okay. Then we have minus a, eta 1 squared, minus a, let's write down eta 1, x1 hat plus a b squared, x hat 3 squared minus y squared. Then you take the square, and we have eta 1 squared here. Okay, so that's the first entry. Second entry is b eta 1, this is eta 1, so we have b times x1 hat plus a b squared, x3 hat squared minus y squared, b eta 1 plus eta 3, eta 3 is y plus y, so that's our second entry for the right hand side. And finally, we have minus b eta 1 minus b, this guy, x1 hat plus a b squared, x3 hat squared minus y squared, minus b eta 1, and that's it. Okay. And this thing, this chunk, although it looks complicated, but it doesn't bother us because the computer will do the computation at each time. This equals g of x hat y. Okay. So it's not at all clear that why this thing should work by just looking at the final result. So it would be a nice, perhaps even fun exercise to take this dynamics that we constructed through Glad's suggestion, put it into MATLAB, pick arbitrary a and b, note that they should be, b should be different than 0, pick arbitrary a and b, and then pick arbitrary initial conditions for x0 and x hat 0, and start the system. And then look at this difference, okay? What you expect here is that this difference becomes 0 at k equals 3 and remains 0 for all future times. In other words, the observer state catches exactly the actual state of the system at k equals 3, because the order of the system was 3 in our case.